And happy Friday morning, March 5th. We are in chapter 23, moving on to enolates and enols. But this is the last day of test two. Make sure you get over there well before the closing time, which is 10 p.m., but the last exams are handed out at 9. So I always recommend you get in there early, avoid the late fee there. Homework 8 will be due on Monday for chapter 23. Look at that, we're moving along. So this will be a 2-class period chapter, not too much there. And then we do have a quiz 6 next week. I think we're moving it back to Thursday. It might be shown on the schedule right now for Tuesday, but we'll move that back to Thursday. And it's not even posted yet, so don't worry about it there. But yeah, questions on that? Any of you guys that are here? Okay. Let's move on here to catch your attention a little bit with enolates. And I always like to show a practical example. Here's a painkiller, Demerol, which is still very popular, used in the clinic. Painkiller, it mimics morphine, so it treats acute pain. It also has the problems of tolerance and dependence and addiction, so it is only prescription use there. But it's a piperidine. It's a 6-membered ring with a tertiary nitrogen in the ring, and then a benzene, and then an ethyl ester on the side. It's simpler structure-wise compared to morphine, but it still has very potent activity hitting the opioid receptor. And I'm showing how it's made. It's made relatively simply, so you can make this on very large scale. It comes from this phenyl acetate ester. So here's an ethyl ester, but I'm showing the enolate. We're deprotonating it already for you. And you can just see one of the SN2 reactions here. And that'll be a hallmark of what we'll be doing with enolates and enols. We'll be using them as nucleophiles and reacting with electrophiles. You need to do this twice. You need to add another equivalent of base, form another enolate, and then do another displacement here. But you see that efficiently forms the 6-membered ring. So how are these two components made? Well, there's a couple of reactions we've covered that you can appreciate there. It comes from this phenyl acetic acid here. We could, of course, esterify with acid, do the Fischer esterification there. There's a little review for you for test 2, maybe. That reaction could be on test 2, right? So there it is, the phenyl acetate ester. And then how do you make that? Well, you oxidize this primary alcohol, and we know how to do that, chromic acid. That'll oxidize the primary alcohol to carboxylic acid. And then how do we make this? The ethyl alcohol with a benzene at that position. Well, we can do the Grignard reagent and then add in ethylene oxide, right? And that epoxide opening. So you can see relatively simple steps to make that part of it. How about the dichloro, this ethylamine there? Well, it comes from 2 equivalents of chlorine plus 2 equivalents of ethylene on methylamine. So you can kind of see how that does. The chloronium ion and then the amine opening up the chloronium ion twice to put that on there. So that's kind of an extension of that halohydrin reaction we saw before with alcohols and chlorine. This is completely analogous. This is chlorine plus a nucleophile, not an alcohol or water this time, but the amine there. Anyway, so here's the main idea for chapter 23, and we'll go over the outline here and show you a little more detail. So we've used so far carbonyls as what? Electrophiles, and we've added nucleophiles to them. And we've covered a couple chapters on that. In fact, all of test 2 is all on that type of mechanism right there. But what you notice, carbonyl compound, if you have at least one alpha hydrogen, you can what? Use base, and we'll have to talk about what type of bases we can use here. We'll learn a couple different bases. We'll form then enolates here, and that's the key thing. This is resonance stabilized. We can draw the resonance structure of that where we put the lone pairs up there, but what type of base we use will determine whether we form it under irreversible or reversible conditions. So you'll see from the outline and the examples today, what we're talking about there. But then here's the paradigm shift. The enolate is now the nucleophile, right? It has high electron density, stabilized by resonance at this alpha position, and then we add different electrophiles to it. So now at the alpha position, we get substituted carbonyl compounds. Completely different, you can say, than this pathway of attack, right? Where we considered that as an electrophile with nucleophiles adding there. So keep that basic idea in mind. This will hold true for the next couple chapters, okay? So in this chapter, we'll look at alkylations and halogenations, and then we'll do other types of electrophiles in the next chapter coming up. So let's see here what we need to see on the outline. You got that up there? Okay, Tyler. Yep. Okay. So yeah, here's the basic idea. We've seen nucleophilic carbonyl compounds before when we talked about tautomerization from enols. So we'll actually start at that point. And we'll start with some equilibrium of different things we've seen before already. But here it is a stronger base. Hydroxide in some cases is strong enough to grab the alpha proton and form the enolate. Now I'm showing the oxygen resonance structure. We could show the resonance structure with the anion right there in carbon. Most of the times the electrophiles will add to the carbon, okay, to give us back the carbonyl resonance in the product. We'll talk in some detail about enolates in general, the reactions, the consequence of this. We'll talk about racemization at the alpha position. We'll talk about halogenation here. The first reaction will be halogenation, yeah. So that'll be a new reaction. We'll form alpha halo carbonyl compounds, and then we'll do some reactions with those. Enolate alkylation, this is probably the more important one. We'll introduce a new base here called LDA, or lithium disopropyl amide. That will be an irreversible, hindered, strong base that will completely form the enolate and then do reactions there. LDA allows us to form the least hindered enolate and have some regioselectivity there, and we'll point that out as well. And then we have the two synthetic procedures here, which are applications of the enolate alkylation from the malonic ester. Remember, oh my, such a good apple pie? Well, here's the M part, malonate or malonic acid. Malonate esters can be deprotonated easily, alkylated, and then decarboxylated. Loss of CO2. We'll have to talk about that. But that allows us to make any kind of carboxylic acid. We're just showing one here. We can put another R group here, a different one if we want to, and make branched carboxylic acids. And then we have the analogous acetoacetic ester synthesis. And this is where you have a beta ketone ester. And then right in between here, you have two hydrogens, just like in the malonate thing, which can easily be deprotonated, form the enolate, and then alkylate readily. And then decarboxylate this one. And the acetoacetate synthesis will make different types of ketones, any type of ketone we want to make. So this opens up some synthetic applications there. We'll look at an asymmetric version here in a minute as well, but let's go back to this and get into the main reactions on this. So a couple things we need to talk about first, and that will be the enolate story. And when we talk about that, we've got a couple things going on, right? We've got this idea that we've already had. We've talked about this equilibrium, right? Where the carbonyl is electrophilic, and we talked about forming the geminal diol. And remember, we said that was highly unfavored, maybe 1% or so. There's another thing going on here, equilibrium-wise, and that's formation of the enol. Okay. Now the carbonyl version is called the keto version, and that also is the one that's highly favored here. But equilibrium-wise, these are going on in the background all the time if the carbonyl compound is placed in water. And both of these are very low, right? 1% maybe. But look at this. Here's the result of it as what? An electrophile. Here's what? It could be a nucleophile. And this could react with electrophiles, okay? So, how can we make that so that that type of reaction would be most efficient now? Well, this equilibrium can be a problem, but in some cases it's actually favored. Let's look at this ketone here, for example. Here's the keto version of this ketone. We have two alkenes here and a six-membered ring. What would be the enol version of this? Well, let's bring the pair of electrons over here, transfer the hydrogen. Oh, what would that be? That would be phenol. Okay. Anybody want to guess what the equilibrium is here? Is this 1% of the enol? Or no, someone's shaking their head. It's actually 100% here, right? And why is that now? This is a special case, right? Here we have what? Aromaticity, right? Highly stabilized. So this equilibrium here, hardly any going back there, okay, if any at all. And we'd say, well, this can easily go over there. And how can we do this? The mechanism here can be pretty simple, right? We can just take a molecule of water and grab that proton, transfer that over there. And you see we regenerate a molecule of water here. And that's under neutral conditions that can easily go, okay? We went over before the mechanism of enol formation from carbonyls under acid or base conditions. And maybe we can review that. But mechanistically, this is pretty simple. Why is this favored now? Well, aromaticity. Normally, these are highly favored over here if they're simple enols, ketones. Why? Because of the carbon-oxygen pi bond resonance, which is more stable than an alkene with a single bond to an oxygen. Okay. Here's another one that we need to point out. What about this equilibrium? So let me draw the enol version of this. And what would be the percentage of the enol now compared to the keto version? What would this equilibrium be? Anybody have an idea? Is this product, is the enol favored? Maybe we can get to that. Who says it's favored here? Who says the keto version is favored? Or who doesn't know? Okay, well, let's look at it. So here is, two ketones, they're beta to each other. But look, when we have the enol thing here, what do you notice now? The alkene, what do we say? It's proximity to the carbonyl. We'd say they're in resonance, okay? Will that be a stabilizing factor, do you think, to have it in resonance? Yeah, most people agree with that. So let me give you the percentages here, and maybe we can rationalize it that way. 76% for the enol in this case, 24% for the keto version. So what would we say here? If we have a special case where we have extra resonance, okay, with these conjugated now, we would say that the enol can actually be favored, okay? And we'll see in a minute here the pKa of these hydrogens are about 10, which is actually pretty acidic, okay? Whereas a normal ketone here, if we think about taking that proton off, that pKa is about 20, okay? So we're going to get into this pKa idea when we talk about forming the enolates and thinking about it. It's a lot easier to form this enolate here. Granted, this is the neutral enol form now with the proton still there. But that resonance idea in this conjugation will actually make this very reactive, and we can pull that off, okay? Questions on that? Kind of a little review of enols and keto versions there. Let's get into the different types of bases now and see which base might be best and why. And we're going to be talking about this same simple ketone, right, acetone. And let's look at this reaction. Sodium hydroxide going to the enolate. And remember, this is resonance stabilized. Plus what? The conjugate acid, which would be water in this case, okay? So we can have the lone pair right here of the enolate at the alpha position, or we can push the lone pair up here onto the oxygen, okay? And, this is a carbanion, we would say. This is a carbon with a pair of electrons. It's negatively charged, okay, once we take off that proton. So, how does it work? Review the mechanism a little bit there. But is this favored or not? We know a couple things here, right? I just gave you the pKa of a simple ketone, which is about 20. And what's the other pKa we need to know here before we can say something about the reaction equilibrium? We need to know the pK of what? Water, right. And anybody remember what that is? Let's see. Yeah, it's 15.7 or something. Let's just say 15 so we can make this easy, okay? So is this favored or not? Drawn left to right there. Let's see, we go in the direction of the weaker acid, so the starting material is actually favored. And we have a little estimate here for the reaction, which would be the one on the right to the power of 10 minus the one on the left. So you see here, this would be 10 to the minus 5, okay? All right, well, that's not favored, right? So this is, as it's drawn here, would be going back that way. Let's try another base. How about sodium ethoxide? Or let's throw in sodium T-butoxide, okay? Our hindered bulky base that we know. There we'd have to change our conjugate acid product, which would be ethanol here. Ethanol pKa is 16. If we did T-butoxide, terpenyl alcohol is 18. Oh, we might be getting better there, right? So what would be our K for these reactions? 16 minus 20, 10 to the minus 4. Getting a little better, okay. 18 minus 20, 10 to the minus 2, okay. So these are still not favored, right? This is a part per 100, part per 1,000, part per 10,000 maybe. Does this mean though, well, it means a couple things, right? The equilibrium's not favored, so this is minor. But does this mean we can never use these as nucleophiles with an electrophile? Is this reaction never going to happen then? That's a good question, isn't it? What do you say to that? It's not favored to form the enolate, but could we still do reactions with electrophiles? Okay, one person's kind of nodding. Maybe it's because I'm I'm nodding too. You guys nod along with me sometimes. Well, why would you say that? Why would you say that that could work? And actually, you could get a pretty good yield of this still too. Because it is an equilibrium, right? You're still forming some of this. And as you remove this from the equilibrium, you'd pull more of it over, okay? So even though this step's not favored, and that might be a high energy thing on the reaction profile, we can still do reactions from that, okay? But these bases here, because it's not favored, we call those reversible bases, okay? So the conjugate acid here could just protonate and go back, okay? So that first step is not favored. These reversible bases are sometimes used, a lot of times not. Let's see some other bases here. How about sodium hydride? NaH. Now that's just a hydride on sodium, right? So what's our conjugate acid there? Oh, it's hydrogen gas, and that's a totally different thing, right? The pK of hydrogen gas is 35. So what's our equilibrium there? 35 minus 20. Now we're getting somewhere. Look at that. 10 to the 15 favored, okay? So if we're using sodium hydride here, we're completely forming the enolate and our byproduct hydrogen gas, okay? So we call this now what? An irreversible base. And that's an important difference now, okay? Now let's do the other one. The important one here is diisopropyl lithium diisopropyl amide, it's called. It has a acronym that we commonly use, LDA, lithium diisopropyl amide. I won't draw it all out. You can see that there, but we have a lithium on here, and what does that mean? Well, the lithium is a cation, and what's on nitrogen? 2 lone pairs and a negative charge, okay? This is a very strong base. We'll examine its pKa of its conjugate acid, see what the equilibrium is. But it's also bulky. It's very hindered, okay? So this will be an irreversible base, okay? A kinetic base, we'll call it, okay? And it's large, so bulky, okay? And this bulk will allow us to form the less hindered enolate and do some selective reactions. So this LDA is important for a few different reasons here, okay? But let's see its reaction here. Let's do LDA as our base here. And what will be the conjugate acid here? Well, it'll be diisopropyl amine, okay? And what's the pKa of an amine? Well, it's 35. Or no, 38. Yeah, let me get the exact number. 38. So it's like ammonia, right? Ammonia 38. And so when that forms, you see that's going to be the highly favored thing. So what's our equilibrium here? Well, it's 10 to the 38 minus 20, 10 to the 18, okay? So you see it's irreversible completely. It's going to deprotonate completely and do the reaction there. So keeping this in mind, these two right here will be the ones we'll use as what? Irreversible bases. These type ones up here, hydroxide, ethoxide, t-butoxide, those are reversible bases, okay? So let's see, let's get into some reactions here and see how things are gonna work. Let's take LDA and use it here. And LDA, we can take a methylated cyclohexanone here, and let's treat it with LDA. And you can get away with minus 78 degrees. That's a chilled dry ice acetone bath. You can really cool that down. Let me say something about the solvent here. It's in THF, which is that cyclic ether molecule, or you can use diethyl ether. You can't use water, okay? No protic solvents here. These are aprotic solvents that we use LDA with, because we're going to be forming the enolate under irreversible conditions, and then we want to use the enolate for a reaction. So if we use LDA here, you have the two isopropyls, negative charge. We have two hydrogens we could possibly remove here. We could form two different enolates, right? Let's see. Well, what if we pull this proton here? Well, we'd form this enolate, okay? And that would be one, okay? And our lithium is there. And the byproduct, the amine, the diisopropyl amine is there. Or what could we do? Deprotonate here, okay? And if we do that on the other side, it's a different enolate, right? O minus right there, okay. Let's look at those two enolates carefully. Which one is more stable if we look at the thermodynamics of this? When you say thermodynamics, it's the ground state energy, difference in stability of the two. Here's an alkene, right? How many groups are on that alkene? 1, 2, 3, 4. It's a tetrasubstituted alkene, okay? How stable is that compared to this here? How many are on this one? Here we have just a hydrogen there, right? So 1, 2, 3. Not too different. Tri-substituted. Which one is more stable in the ground state? And we said this before with Zaitsev's rule in 351. We always formed the more stable or more substituted alkene, right? Which one's the more substituted or more stable enolate in this case? Well, this one, the one on the left, okay? By about 5 to 6 kcals per mole. But if we're at low temperature here, what can we say here? Here we have a large, bulky base with these two diisopropyl groups. How easy is it to get in here past this methyl group here versus getting in here, you know, on this side you just have the two small hydrogens, okay? So in this case, with LDA, this is 99%. This enolate at low temperature, 1% here. But wait a minute, that's the more stable one. Why are we getting so much of the less substituted, less stable enolate in this case? Well, it's the bulk, okay? The bulkiness, the large size of the LDA allows us to form this. So we're going to call this more substituted, more stable, okay, intermediate. We're going to call that what? The thermodynamic enolate. Okay. What are we going to call this one? The kinetic enolate. Why do we call it kinetic? Kinetics refers to what? Not the stability of the resulting thing, but kinetics refers to what? The speed or the rate that it's forming. So this one's forming faster, okay? Forms faster, you could say. This one forms slower with a bulky base, okay? Now, let's look at this enolate. Let's do the same thing here, but with sodium hydride, okay? Now, which one is going to be major? Well, it's 95%. This one, and only 5% that one. Again, this is an irreversible base, okay? This completely forms the enolate. So the arrow as it's drawn here is true. But what about the size of this? This is just hydride, right? That's very small compared to TB toxide. So we've got the two extremes here, which is nice, right? If it's small enough, it's able to grab this hydrogen at the more substitute spot and form the more stable thermodynamic enolate. So we call this an irreversible thermodynamic base. This is our kinetic, okay, strong irreversible base. And it's good to have those two there because of the reactions now. What are we going to do here? Let's do some other reactions here. And look at maybe the consequences of being able to form an enolate. And this is kind of a trivial reaction, really. It's kind of just an equilibrium thing. We're not really forming, well, we are breaking a bond and then reforming things. Well, we'll see here. This is the R enantiomer of this chiral methyl ketone. You see the stereocenter there. The optical rotation is plus 72. So you can measure that in the polarimeter. But then we put it in sodium hydroxide, or we could put it in acid and water. So these are what type of conditions? These are reversible conditions. It's not a super strong base compared to LDA or sodium hydride, but it is strong enough to form some enolate, okay, a tiny amount at equilibrium. But let's follow the optical rotation here. In fact, you can do this experiment right in the polarimeter, and you can watch this optical activity eventually go to 0 after about 4 hours. Okay. What happened here? The optical activity is now 0. What does that mean? Is it enantiopure? Is it all R now? No, what is it? If this is 0, this is now racemic, right? And you have a 50-50 mix of the R and the S. So can we figure this out? And this is a consequence of having a stereocenter next door at the alpha position to a carbonyl. Okay, so what can occur here? Who can help us out to figure this out? Is there a mechanism we can invoke for this? So what would we need to do with hydroxide to rationalize this outcome? Have to use the hydroxide to remove the hydrogen, right? And if we did that, let's see what would happen. We'd have the enolate, and we can, invoke the resonance structure here. But look, we just took the hydrogen off there, right? You could say, well, we still have 4 groups on that carbon. You could say, well, and maybe if we just put the hydrogen back on the same place, it would stay R. Right? Well, what happens when we do the resonance structure here? Well, let's see. Well, there you go. Is that resonance structure chiral anymore? What happened to that stereocenter? Just went away, right? This is now sp2 hybridized, right? And then what? Let's see. Well, we've got water in there, so this is reversible formation. So if we have water in here, what can occur? We can attack either from the top or from the bottom. And what's the probability of that, top or bottom? Now, 50-50, right? So we can easily racemize stereocenters that are alpha to carbonyls if we think about this a little more carefully. So there's a consequence for it, for that going on there. All right, let's get into some alkylation chemistry now. And we're going to use our LDA and sodium hydride. We're going to get into some of these reactions. Key reaction is going to be the alkylation reaction. And we will do the outline, don't worry. Let's see, LDA. So what can we form? We can form the enolate. And you can draw either resonance structure of the enolate. Okay, if you want to draw this one, that's fine. But it's going to be nucleophilic on carbon, not on oxygen. Okay. So the next step, we put in methyl iodide. And what? We can put in primary or secondary, but it has to be sp3 hybridized. So what type of reaction is this? No sp2 and no tertiary. So what type of reaction is this? Here we have a charged nucleophile, right? So we can relate this to a previous reaction, right? Bimolecular kinetics, it's a substitution. We have a strong nucleophile. So what are we going to call this reaction, really? It's the same thing we saw before in 351. What is it? It's what? SN2. Yeah, very good. So we're doing an SN2 reaction. This is all the hallmarks of that. Let's bring the electrons down, attack here, and there's our leaving group. The iodide, same leaving group we saw before. And what's our product? The ketone. Okay. Yeah. So alkylation reactions with that. Let's do another electrophile here. We could do allyl bromide. And if we did that, we get this. Okay. Yeah. So that bond right there and there at that alpha position, we can do that substitution. How about with esters? Now, esters are a little bit different. It's got an oxygen over here. Here the pK was 20. Esters are a little bit higher, 25. And that's because you already have resonance here, pushing electron density by resonance in here. So it doesn't have as much stabilization power as a simple ketone. But still 25 is easily overcome by the LDA, right? So it's still favorable here. And the enolate looks like this, but of an ester now. And that's okay. Looks a little funny. There's two oxygens on there. But yeah, let's do the same reaction here with allyl bromide. And what would we get? The ester with the allyl group on it there. Very high yield. Okay. Let's do a little bit more substituted reaction. Let's have a cyclic ketone. And we're going to put on that same allyl group. So LDA and allyl bromide. What are we going to get? Well, the two sides are the same. Doesn't matter which side we form the enolate on, and we're going to get the product. By the way, we're forming a stereocenter, but it'll be racemic. The R and the S are both going to be there. What can we do now? Well, let's do some more LDA and more allyl bromide. Now, what? We already have an allyl group on there. Which side are we going to deprotonate with the LDA? And this is an issue of regioselectivity. Okay. What type of regioselectivity are we going to get? This is a bulky, large base, right? So we're going to pull this one on the right or the hydrogen on the left. How many say the one on the left? Okay, yeah, that's the smaller one. And that'll be the kinetic enolate, you see. And then when we put in our allyl bromide, we'll get the allyl group over there, and we'll get that product. High yield. Let's do the same reaction here, but with sodium hydride and allobromide. Now, we don't have to use the same electrophile. We could use a different primary or secondary halide, right? But now we're using sodium hydride. This is also an irreversible base. The question is regioselectivity, the first idea. Are we going to pull the one on the left or the one on the right in this case? How many say the one on the right? Okay, yeah. And that's because what? This is the thermodynamic base now. Let's look at the enolate structure. It'll look like this. And then when we alkylate there, you see, the nucleophile stays right at that position where we form that enolate. So what's going to be our product? Well, there'll be two allo groups on here. Okay. Very different products. These are complementary regioselectivity, we say there, forming them in a different spot there. Okay. Here we could have used sodium ethoxide. And even though this is a reversible base, it would have also gone under thermodynamic conditions. These reversible bases will tend to be thermo also. And even though the equilibrium is not favored in that case, enough of it would go here. And, you know, with the excess allobromide, you get this product also in pretty good yield, okay? The better one, I think, yield-wise, is the sodium hydride, but you could use this reversible one also there. All right, let's do halogenation next. And then, yeah, I will go through the chapter summary here, but yeah, we're kind of reversing that. So stay over here right now for the time being. Let's see. Want to do halogenation now. And this is where we're going to have a halide molecule of halogen here. And it's different conditions, right? This is just water, and it works better with a little bit of acetic acid in there. And the actual intermediate here in this case is the neutral enol, okay? So, you know, in the alkylations, I was emphasizing the enolates, but under these conditions, it's actually milder. You don't need to use an expensive, bulky base or whatever. You can use the enol. And then when you form the enol, you see, with chlorine or bromine, and it will be limited to those two, like we saw before. Fluorine's actually explosive. We avoid that. Iodide, carbon iodide bonds aren't very stable, but those are okay. You can use the material there. You can see we can just bring down the pair of electrons, attack here. So the rest of the mechanism's okay. You see the protonated form of the enol. You see X minus here. And then where does this end up? Well, water can take that off or whatever. And you get to the halogenated product here, and this thing gets acidic. So you need to neutralize that acid at the end. But this is okay. We can get good yields of this. So let's see the one here with bromine under these conditions. You can get a good yield of bromoacetone. Let's take cyclohexanone with chlorine and a little bit of acetic acid in water. And, you know, the acetic acid helps out the formation of the enol. So let me show a little bit of that mechanism to remind you. So that'll get to the enol, right? We've done that mechanism already. And then let's just go ahead to the halogenated product. So we'll go to that, okay, the halo product. And one more, how about a aldehyde? Now it's always at the alpha position, and that's over here on the other side. That's not the alpha hydrogen, that's right on the carbonyl. So if we brominate this in water, and you don't have to have the acetic acid in there, it'll go a little bit faster if it's acidic. So that's kind of like the imine-enamine formation kinetics. Bromine, yeah, and that would be our product in good yield. So yeah, we get the monohalogenated products and the enol for that case. Let's look at the same conditions here, or same reaction, but under basic conditions. So we're going to halogenate, but we're going to use base. And there'll be a little bit different conditions here. Yeah, so let's take this ketone first. Ethyl phenyl ketone. And let's react that with bromine and base in water. And the problem here is not the formation of the enolate, it's the over-halogenation. So both hydrogens here that are alpha, and there are only two that are alpha, both get halogenated here, okay? Now we are forming the enolate, so let's grab a hydrogen here. And the mechanism is different that way, right? It is the enolate. And then our electrophile is bromine. So we are brominating once, okay? And let's see, what's the story here? Well, that's not the product in this case, okay? So this implies excess here. In fact, even if you limit the amount of bromine you have, a lot of times as soon as some of this forms, look, you can form the enolate again, right? And what's going on here? Well, another equivalent of base can pull that proton off. And what? This is inductively electron withdrawing, right? The halogen. So that will actually stabilize the enolate. This is a slow step here, okay? So actually, once you get one bromine on there, the next enolate, which would look like this, is actually favored now, okay? And that leads, you see, to the di-brominated product. So this over-halogenation is a problem under basic conditions. But let's look at acidic conditions here. How come acidic conditions don't favor that? Well, acidic conditions, if we got one on there already, okay, and we're trying to form the enol that has a halogen already on there, you see, we're trying to protonate this, right? We're trying to add more acid here. And if this is electron withdrawing on this product here under acidic conditions, the slow step is forming the enol again. If we're pulling the electron density out of here, this becomes slower. Okay? So under the acidic conditions, it actually always favors mono. Under basic condition, it always favors over alkylation because this is what? An enolate being formed under anionic conditions, and this stabilization will actually make that faster. So it's kind of a subtle point, but it has to do with the rates of the enol formation being slower in this case if you have a halogen, or the enolate being formed under basic conditions actually faster in those conditions. Anyway, like I said, it's kind of a subtle point. Don't worry about it too much there, but it does point out the differences in the halogenation condition reaction. Let's look at the utility of these halides. So if we can form these, we just formed the monobromo, and we can react that further with lithium carbonate base. And lithium carbonate's the one pointed out in the book, and we'll stick with that. There are other bases that can do this. TB toxide, for example. This base is strong enough, actually, to do this. So we can go to enones, okay? We saw enones before with cuprates. So once you halogenate the alpha position, you can eliminate with lithium carbonate. Or you can react it with a nucleophile. How about potassium cyanide? Well, then you get an SN2 reaction. You'll get the alpha cyano one. Or one the book points out is the nitrogen. Here's benzylamine, primary amine, and you can make an amino, alpha amino group there. There's a little bit more to that mechanism. You got an attack here. You initially get an ammonium cation. In the presence of more base, you can take that proton off, adjust the pH if you need to give the neutral amine product there. Yeah. One other reaction to point out here with the halogenation, and I'm not sure I even want to do it, but let's point out the haloform reaction. And yeah, we will go back to the overhead here in a second. I'm not going to belabor this reaction. It's called the haloform reaction. It's typically done with iodide. Let's do this one, which is methyl ketone iodoform. Iodoform is this molecule, triiodomethane. So we have excess iodide, basic conditions, okay? So that's what it is there. And the product is this. And this will seem kind of crazy, but there it is, okay? And what you can see is excess iodide. We are over halogenating this methyl ketone, and it has to be a methyl ketone. So here we got 3 iodides on there. And how do we get to this? Well, we need to use the base again to do something here, right? This adds here, actually. And from that tetrahedral intermediate, we'll actually break this off and then protonate the triiodomethyl anion. And this only works, we're breaking a carbon-carbon bond here because of the stability of this, okay? So once you have 3 halogens on here, you can actually have a stable, non-resonance stabilized methyl anion. I'll let you read about that and look at that. It's not preparatively useful. Look, we're going to a carboxylate from a methyl ketone. That's actually a simpler molecule. So there's no synthetic applications of this. It used to be done as a test for methyl ketones because this is insoluble and it's yellow. So I'd use it as a test for methyl ketones in the old days. Well, we can tell those now by NMR just fine. We don't need this reaction. So if you want to look at that reaction, that's fine. So yeah, we did halogenation and alkylation, and we'll of course review that on Monday, but we will get into the rest of these topics here, including the malonate and the acetoacetate synthesis. I wanted to show you this application here. We talked about, getting racemic products there. You can do alkylations with a chiral enolate. This enolate right here is an acyloxazolidanone heterocyclic structure. You can deprotonate there with LDA, form a lithium enolate. And look, there's a benzyl stereocenter right here. It actually comes from phenylalanine, an amino acid we'll see later. And this will alkylate from this top face here selectively with primary, secondary halides and get 1 stereocenter there. Well, with high selectivity, greater than 20-to-1 selectivity. And then you can take off the chiral auxiliary. This is just on there temporarily. It's called an auxiliary. You take it off and you see you got the enantiopure now with the stereocenter, chiral carboxylic acid. Or you can take off the auxiliary with LAH, add hydride, tetrahedral intermediate, you'll have the oxazolidanone come off, and you'll have a chiral enantiopure alcohol. This revolutionized asymmetric synthesis, being able to do these alkylations selectively. In fact, it opened up the synthesis of this molecule right here. It has a long name. Methyl BMT, I'll call it. It's an amino acid. That's a hydroxy group and this group here. And you notice it starts the synthesis up here with an asymmetric alkylation. And there's many steps to make it. But this key intermediate here, enantiopure now, went into the synthesis of a very important drug called cyclosporin. And what are these drugs for? Well, it's an immunosuppressant. And maybe you've heard of those before. Why would somebody want to suppress their immune system? That seems like a negative thing to do. Well, if you undergone an organ transplant, your immune system tends to reject those organs, even if it comes from a close relative here. So You suppress the immune system with this guy. The mechanism of how it works is pretty well known. It inhibits T cell proliferation here. It's a common clinical drug. So when a person gets a kidney transplant, for example, you need to keep this substrate or this target of cyclosporin here inhibited. And this is a complex cyclic 11 amino acids here in a ring. And the thing that used the asymmetric alkylation is this unnatural amino acid right here. You have to have that one in there to have this drug be potent enough. So this alkylation here turned out to be the key thing for opening up that organ transplant. And the poor people have to take these immunosuppressants the rest of their lives to keep the body from rejecting that organ. So it can be a pretty onerous thing for them. But anyway, so yeah, that's alkylation there. And like I said, next time we'll get into the malonic ester synthesis, which also is alkylation stuff. We'll have to talk about pKa's again. And the new thing there will be decarboxylation. We'll eliminate a molecule of CO2 from the malonate or from the beta keto acetate to give ketones or carboxylic acids, okay? So mechanistically, it's not too bad. And it really is just the two new reactions, enolate alkylation and enolate halogenation that we'll see there. So very good, guys. Good luck on the test today. And we'll see you on Monday, actually finishing up 23. So no rest for the weary there this weekend. Make sure you're read up through 23. I appreciate that. Okay, guys, we'll see you next time. Thank you.